Good morning. Today we are going to discuss how X-rays are generated. Have you ever wondered how doctors can see inside our body without any surgery, or how scientists determine the crystal structure? Answer lies within X-rays. In this presentation, we will discuss how these powerful rays are generated right from the acceleration of the electron to their sudden deceleration on the metal target. Now let us discuss how the X-ray were discovered. They were discovered by German physicist Wilhelm Röntgen. You can see his picture here, and he was discovering how the some of the minerals interact with the light which was produced by cathode ray. Now, one day he noticed that a piece of the fluorescent paper glowed whenever the tube was on, despite being outside the cathode ray tube and quite far away. As cathode rays are known not to travel more than a few millimeters in air, glowing of that paper must have been caused by a new type of ray, which he called X-ray. Now he discovered that X-rays are of wavelength 1 angstrom, which means that the wavelength is very small and the energy is high. Such high energy radiation should be handled with proper carefulness. Now here is the picture taken of a palm using X-ray, which such pictures were not possible to take before the X-ray were discovered. So X-ray has helped in many ways in medicinal chemistry as well as in material chemistry to know the structure of various crystals and various the genetic coding material which are present inside our body, so complex structures such as ribosomes. So X-ray has been discovered, and since they were discovered they have been a lot useful in understanding many of the materials. And here you can see some uses of X-ray, like airport security. It is a very important nowadays, which has been possible because of the X-rays. In a very small time we can detect what people are carrying inside their bags without actually taking the materials out of the bag. So X-rays have been very useful since the day they have been discovered. Now let us discuss the ways to generate X-rays. Um, Here you can see the basic setup to generate an X-ray in a glass vacuum tube. Now it mainly consists of two electrodes, a cathode and an anode, sealed inside vacuum. The purpose of vacuum is to prevent the electron from colliding with gas molecules, allowing them to travel freely from cathode to anode. Now the cathode is a tungsten filament. Here is a cathode, which is a tungsten filament housed on a focusing cup made of molybdenum or nickel. When the filament is heated by passing the current, it emits the electron through thermionic emission. These electrons are then focused onto a narrow beam and directed towards the target anode. Here you can see the anode, which is usually tungsten anode. Now why tungsten? Because it has a high atomic number, so it produces high energy X-rays. It has a high melting point which can withstand intense heat, and it has good thermal conductivity to dissipate heat efficiently. Now sometimes the target is mounting on a rotated anode to spread the heat over the larger area and prevent damage. Why the heat is generated? Because X-rays are generated when these filament electron are collided with the anode target. So due to this collision, heat is released, and due to this heat sometimes the intensity of heat increases so much that the target anode starts to melt. So usually the solution of this is to use a rotating anode. The rotating anode rotates, and suppose this is the point, it is hit by the electron. Now it is hit by the electron, it is heated, now it is rotating, so the electron is hitting all over these points, other points on the anode, and this point has been hit earlier. So this point has some time to get cooled and return to the same position where it has to get hit by the electron again. So the purpose of rotating an anode is to give a particular space on the anode some time to cool off before it is hit by the electron again. So when between these cathode and anode, high potential difference is applied, typically 30 to 100 kilovolts. This accelerates the electron emitted from cathode toward the anode at extremely high speed, nearly approaching a significant fraction of the speed of light. Here we can see the anode being hit by the electron generated by this cathode. Now, when these high-speed electrons strike the tungsten target, they undergo sudden deceleration. The kinetic energy of these electrons is then converted to two things: heat and X-rays, 99% heat and 1% X-rays. Now, even though the X-rays are small fraction of total energy, they are extremely powerful. Now, here you can see the cooling part. It is the another simplified diagram of this X-ray production, and we can see the cooling part. Since most of the energy is converted into heat, a cooling system, often a copper block with circulating water or oil, is attached to the anode, prevent overheating and damage to the target of the anode, which is present here. Now we can see a small animation how the electron hit and the at the target anode to produce X-ray. Here you can see, as the potential difference is applied, the electron from this filament goes and hits the anode, generating the X-ray, which is emitted through this tube through this small window. Now the generated X-ray exits through a beryllium window, which allows the X-ray to pass but absorbs minimal radiation, ensuring the emerging beam is clean and intense. Now let us see how the electron travels fast as the potential difference is increased. The speed of the electron hitting the target anode increases. Here you can see again, as the potential difference is increased, the speed increases, and due to this deceleration, it decelerates. Decelerates means the speed of the electron as well as the path of the electron after hitting the anode changes. So speed decreases, so deceleration happens, and deceleration also happens in two ways. First, it can interact with the atom's nucleus of the anode, and secondly it can interact with the core electrons, which we will discuss in the next slides. So for now you have to see that high potential difference, as the potential difference is increased, speed is increased, and the X-rays are generated with the more intensity and fast. Let's go to next slide. So let us discuss about the microfocus X-ray. In earlier we have seen that X-rays are produced in a glass tube, but in a conventional hot cathode or a rotating anode X-ray tube, only those X-rays are emitted which are in correct direction that can actually reach the crystal for diffraction. Why? Because X-rays are emitted in all the direction from the anode, but only a narrow cone is aligned with the crystal. Hence most of the generated X-rays are wasted. This reduces beam intensity and efficiency. Now, to overcome this loss of X-ray, optics are introduced to collect X-rays emitted in many directions and focus them onto a crystal. Why? Because optics work like a lens system. They gather the scattered radiation and convert it into a single intense beam. This way, X-rays that would have been lost can be efficiently used, giving higher intensity without increasing power. This focusing system works only if X-ray originate from a tiny emission spot called a microfocus source. Why? Because if the X-ray come from small point, all emitted rays can be geometrically focused on one target, and a large source would blur the focus and reduce resolution. Now two main focusing systems are used. One is ellipsoidal X-ray mirror and the other is bundle of hollow glass fibers. Both are shown here. So let us talk about ellipsoidal focusing mirror. These mirrors have special curved shape. You can see the special curved shape that reflects the X-ray from one focus of the ellipse to another. The second focus is where the crystal is placed. Why? Ellipsoidal geometry naturally directs the divergent X-rays into a single focus point, increasing the beam intensity. Now, for the bundle of glass fibers, These are capillary optics, tiny hollow tubes that channel the X-ray through total external reflection towards the crystal. Why? Because each capillary acts like a light guide, combining the multiple reflection to deliver more X-rays in one direction. Such a larger fraction of X-ray emitted by anode is now collected and used in the used, and the electron current can be reduced without sacrificing the beam strength. Why? Because lower current means fewer electron hitting the target, less kinetic energy, and then less heat is generated. Some designs have become so efficient that even no cooling is required. So, which I have not mentioned here, there is multi-layer X-ray mirror which are made of tungsten and silicon. These mirrors have alternate thin layer of tungsten, high atomic number, and silicon, low atomic number. Why? The alternating layers create constructive interference for the specific wavelength of X-ray, just like Bragg reflection in crystals. This enhances the reflection of certain angles, improving the mirror efficiency. As the mirror is curved, the incidence angle changes along its surface, so the layer thickness is gradually varied. Thickness layers where theta is smaller, thinner where theta is larger, ensuring that Bragg's law is satisfied everywhere. The X-ray diffractometers are enclosed in a shielded cabinet with windows made of plexiglass impregnated with heavy metal salts. The X-rays are highly penetrating, so cabinet prevents the radiation leakage. The heavy metal salts, like lead compound, absorb the stray X-rays effectively. Plexiglass provides a transparent and durable shield, allowing us to observe the safety while blocking the harmful radiation. Here you can see an actual microfocus X-ray source with all the phenomenon we have discussed happening in its inside, and the high intensity X-ray beams with a very small wavelength is produced through this hole. Now let's discuss the physics of how X-rays are generated. So X-rays, the principle of generation of X-ray was to release electrons from a cathode, tungsten filament, high energy, which strikes the anode surface, decelerates, and this is how X-rays are produced. Now this deceleration occurs in two ways, which give rise to two type of radiation. First, having a broad and continuous background called white radiation, and second, having sharp peaks called characteristic radiation. Now, white radiation. These are produced by deceleration of electron as they interact with the atoms in the target. Now, when the electrons coming from the cathode goes to anode target, it interacts with the atoms, more precisely the nucleus of the atom, and it decelerates, changes its path, changes its speed, and due to which X-rays are generated. So because X-rays lose different amount of energy depending on how close they pass to the nuclei, different types of wavelengths are produced, because different types of energies are generated which are lost. So because of this, a continuous spectrum is obtained, and the maximum photon energy correspond to an electron losing all its kinetic energy in one collision, because the more energy it loses, the more X-ray is the more intensity X-ray is generated. Now the typical voltages are 30 to 60 kilovolt, giving us the minimum wavelength of 1 angstrom or less than 1 angstrom. And the source of white continuous X-rays it is, and the energy depend on accelerating voltage and not on the target material. Dominant processes when electrons are not energetic enough to cause the inner shell ionization, this type of radiation is generated. The second type of radiation that is generated is characteristic radiation. Why it is called characteristic radiation? Because it is not dependent on the voltage but is dependent on the target anode material. Now it occurs when the incident electron knock out the inner shell electrons which are present in the core orbital. The outer electron falls into the vacancies created inside the core shells and emit the X-ray of fixed energy. The energy difference between these two orbits lead to characteristic wavelength generation, which is given by this formula. Now, how they are sharp in nature? Because when the electron are emitted from core shell, the coming electron from the cathode collides with the inner shell electron, it is knocked out and vacancy is generated inside. Now a electron from the outside shell comes to inside in that vacancy, releasing some energy because its energy is lowered, and this released energy is X-ray, and it is called characteristic because the energy released is equal to the energy difference between the two orbitals which are involved in this transition. So because the involvement of energy is very precise, so precise wavelength is generated and giving rise to sharp peak. That is why it is called the characteristic radiation. Now in this small animation we can see how these are generated, these two type of radiations. Sometimes the wide radiations are called, which was given the name here, the Bremsstrahlung radiation. It is also called wide radiation. It is a German name. So there is the nucleus and there is the outer shell electron orbit. So this is the coming from from cathode and being deflected as they interact with the nucleus, and being deflected its energy is decreased, and due to its energy is decreased, some energy is released, and that released energy is X-ray. Now this was the first phenomenon giving rise to a continuous spectrum of white radiation. Now for the characteristic radiation, you can see here the electron is coming from the cathode filament interacting with this atom of anode, knocking the electron from the core shell of the anode atom. So the vacancy is generated from outer shell, the electron are coming inside, and due to this energy of this electron is decreased, it releases energy in the form of X-ray. And as you can see that the difference is the energy is very precise, so the energy released correspond to the difference of the energy between these two orbitals, and that is why the wavelength is very precise. So this is the two type of radiation which are produced in X-rays, in the form of X-rays. So we can say that the continuous radiation, which is the white radiation, is due to the deceleration of electron, which is caused by interacting with the nuclei of the anode target atom, and the characteristic radiation is due to the inner shell transitions, which is dependent on the target, and continuous radiation is dependent on the voltage which is applied externally. And high atomic number elements of the target anode creates high energy shorter wavelength X-rays. Now, as discussed earlier, we can discuss the graph for white and characteristic radiation wavelength. So here is the X-ray intensity and here is the wavelength, and we can see that the white radiation is a broad spectrum consisting of many, from 1 angstrom roughly to 3 angstrom, giving a maxima at this position. It includes many wavelengths, and the K alpha, K beta, which are the denotations of characteristic radiation, which we will discuss in next slides. So this is the sharp peaks corresponding to a very particular wavelength on the x-axis. So these are the characteristic radiation dependent on the target anode material, and this is the white radiation which is dependent on the external voltage. How you can see that as the external voltage is increased from 5 to 25 kilovolt, the intensity of white radiation also increases. Now let's discuss about the Singbank notation, which is a system used to name different X-ray spectral lines. This notation was introduced by the Swedish physicist Main Singbank to make the naming of X-ray lines simpler and more systematic. Instead of giving complicated electronic transition number, he assigned short symbols like K alpha, K beta, which we can see here, K alpha, K beta, which is also shown here, the transitions. So in this system, the letter, the capital letter, which is also example in this example is shown, the capital letter K, L, M, N, etc. represents the electron shell where the vacancy is created, that is the shell to which the electron transition ends. For example, the K series, which is here, correspond to the transition ended in the K shell. From we can see from any of the above shells, the transition is ending in the K shell. Also for the L series correspond to the transition ending in the L shell, which have a principal quantum number of 2. The Greek letters such as alpha, beta, gamma indicate which higher shell the electron comes from. K alpha means the electron fell from the L shell to the K shell. K beta means the electron came from the second highest energy shell, that is the M shell to the K shell. Similarly, K alpha correspond to the transition from M shell to the L shell. Now, here you can see that in K alpha and K beta, 1 and 2 are also shown. It shows that even one type of transition, that is K alpha, there is slightly different energy level which are shown here as 2 and 3. These slightly different energy level arising due to spin orbit coupling also give rise to different spectral lines, which is not much differentiated in their wavelength, but yet also they are different spectral lines due to hyperfine splitting of the subshell. Now let us learn how to interpret the information from any denotation of the spectral line. Like from K alpha, we know that from K alpha it means that the electron spectral transition is ending in the K subshell, which means that the electron is coming to the principal quantum number of 1. And as in principal quantum number 1 there is the L value is 0, yani ki, which means that the subshell which is present in this is only S. So it is denoted by 1s. And alpha means that the electron to fill the vacancy is coming to from the next highest energy, which is L, with respect to the K, next highest energy with respect to K, which means L. And L has the principal quantum number of 2, which contains two subshells 0 and 1, which means 0 corresponding to S and 1 corresponding to P subshell. And keeping in mind the electron transition rule, the transition rule says that the value of delta L, which means that the difference between the azimuthal quantum number between the two orbital in which the transition is taking place, has to be plus minus 1. It cannot be it cannot be 0, it cannot be plus minus 2, it has to be plus minus 1, which means of the two 0 and 1 subshell, the electron is coming from 1, that is the P subshell, to 0, that is the S subshell, because it cannot come from S to S because the value of delta L will be 0, which is not allowed, which remains us with P, which means that the electron is coming from the P subshell of the second principal quantum number to the 1 S subshell or 1s orbital, because it contains only one orbital, 1s. So that is why K alpha means that the spectral transition is taking place between the 2p and 1s orbital of the atom, which give rise to the X-ray characteristic radiation. Now if we come to discuss about K beta, what information does it give? Again, K means that the electron is coming to one principal quantum number having the value of n1, containing only one subshell, which is S, which means that 1s orbital, it is coming to 1s orbital. From where it is coming, it will be given by this beta, which means that the second next highest energy level, which means that M, it is coming from M subshell to K, M shell to K shell. And again, keeping in mind the selection rule, it can only have value of delta L plus minus 1, and M, which have the value of principal quantum number as 3, can have 3 values of the subshell, which is 0 corresponding to S, 1 corresponding to P, and 2 corresponding to D. Now the transition cannot take place between S and S, which means that delta L will be 0, and also the transition cannot take place between D and S due to because the value of delta L will be plus minus 2. So which leaves us again with the P subshell, and which means that the transition is taking place from 3p to 1s. So from K alpha we have concluded that the transition is taking place between 1s and 2p and 1s, and the K beta gives us the information that the transition is taking place from 3p to 1s, which give rise to the characteristic radiation of X-ray. Now the K alpha 1 and K alpha 2 means that the splitting of the orbital. Sometimes the splitting of the within the orbital take place, hyperfine splitting, due to the spin orbit coupling, and which means that the p subshell is split into two shells or orbitals, we can say, that is 2p 3 by 2 and 2p 1 by 2, and the transition can take place if it is K alpha, which means that the 2p transition is taking place between 2p and 1s, and within the 2p the transition can take place from 2p 3 by 2 to 1s 1 by 2, and from 2p 1 by 2 to 1s 1 by 2, giving rise to K alpha 1 and K alpha 2 spectral line. So this is how Singh-Band notation gives us the idea about the characteristic radiation of X-ray spectral line, that how the different anode atom can give the anode atom, which means that it tells us about the orbital of the anode atom, target anode atom, between which the transition is taking place to give rise to specific X-ray radiation. So Singh-Band notation tells us which electron shell are involved in the X-ray transition, that is from which shell the electron falls and to which shell it goes, to give rise to a X-ray spectral line. So now we will see how that the energies of the characteristic X-ray increase as the atomic number of the target increases. By the example of copper and molybdenum, if we compare the same type of wavelengths of these two material that is generated, the X-ray or generated by these material, the copper gives the wavelength longer and molybdenum gives shorter. That is because the molybdenum have a higher atomic number and copper have a lower atomic number. The copper radiation has a cleaner spectrum and longer wavelength than molybdenum. Longer wavelength are more strongly absorbed by the crystal and give rise to diffraction pattern in which the beams are separated farther apart, because they have the longer wavelength, and longer wavelength are separated gives the diffraction pattern which have beams farther apart. But the molybdenum being higher in the atomic number, it gives the diffracted beams which will be closer together, and it is therefore useful for measuring the smaller unit cell, because the beams will be closer together and there will be more to measure. Also, the molybdenum radiation is weakly absorbed by the atoms with the atomic number larger than 25, and that is why it is useful in determining it is useful for determining the structures of the crystal with smaller unit cell and heavy atoms. Heavy atoms because the heavy atom do not absorb much of the molybdenum radiation, which means we can get a cleaner spectrum without these heavy atoms to determine the structure of the crystal. The crystal in which the heavy atom information is not required. We use the molybdenum as a target. So, as we know that when characteristic X-rays are generated, we usually get a set of lines, mainly K alpha and K beta. Now the K alpha line itself is actually made of two very close spaced components, which we have discussed earlier, K alpha 1 and K alpha 2, which was coming from the same subshell due to the orbital splitting. So the difference in their wavelength is less than 1%, which is so tiny that for diffraction experiment we can treat them as their single wavelength. Experimentally, both these lines are used together and we take an average wavelength called the K alpha line. We are talking about the K alpha 1 and K alpha 2. The weight average wavelength is calculated by the formula which is given here. Now, as we know that K alpha 1 is about twice as intense as K alpha 2, the weight average in this formula of average wavelength of K alpha, we have taken twice of K alpha 1 and only one multiple of K alpha 2. However, the K beta line has a different story. Its wavelength differs from K alpha roughly by 10%, which is significant. Because the diffraction angle depend directly on the wavelength, both K alpha and K beta radiation produce separate diffraction patterns, slightly shifted in position. So because the difference in the wavelength in K alpha 1, K alpha 2 is very small, we can treat them as monochromatic radiation because there is not much difference in the diffraction pattern generated by combining of these two wavelengths. But it is not the case in K alpha and K beta because the difference is more than 10%. They both produce separate diffraction patterns which are slightly shifted in position. So this overlapping of pattern can make it really difficult to measure accurate intensities. So to avoid this problem, we usually filter out the K beta radiation, keeping only the intense and useful K alpha radiation. Now this filtering is done using X-ray absorption filter. X-ray absorption filter, by using this we can filter the K beta radiation out of the K alpha radiation. The basic idea is that the X-rays of shorter wavelength are more penetrating and get less absorbed as their wavelength decreases. But there's an interesting point. As in this picture you can see, we have discussed that as the wavelength becomes shorter, the energy increases and the absorption decreases because it can penetrate more easily. Here you can see as the wavelength decreases, the absorption decreases like this. But the interesting point here is this vertical line. What is this? When the energy of X-ray becomes high enough to knock out the electron from the K shell of the absorbing material, the absorption suddenly increases sharply, which is shown here. This sudden jump is known as the absorption edge or resonance energy. This is the absorption edge or resonance energy. So, and after this sudden jump, the as the wavelength is decreased, energy increased, the absorption is decreased as expected. For example, in a copper absorber in which the target is a copper material, this jump occurred near 1.38. This is basically shown of a copper target metal. The jump occurs near 1.38. So now if we choose another material whose absorption edge lies between the wavelength of K alpha and K beta of copper, it will absorb K beta much more strongly while letting most of K alpha pass through. As you can see in this figure, this shows the radiation produced by copper. So this is the K alpha radiation of copper, this is K beta, and this is the white radiation which we have discussed earlier. So we don't need K beta or the white radiation. So what do? We choose a material, another material which has the absorption edge between the K alpha and K beta, and this is exactly how the nickel filter works for copper radiation. The nickel has an atomic number of 28, just one less than copper, which is 29. Its absorption edge falls perfectly between the K alpha and K beta radiation of copper. So the nickel filter absorbs K beta radiation about 6 times more strongly than it does K alpha. Here you can see it the absorption edge of this is the nickel. It lies exactly in between K alpha and K beta. So here we have discussed earlier that the K absorption edge occurs when the radiation of where the energy of the X-ray becomes high enough to knock out the electron from the K shell. So here the energy has become high enough so that the absorption suddenly increases, and it increases in such a way that it absorbs the radiations coming after this absorption. So after this the white radiation comes and the K beta comes. So in this strongly absorbed radiation, when the K absorption edge comes, the absorption increases. It absorbs all of the radiation which comes after the K absorption has reached. and almost passing all of the radiation which has come before the absorption, K absorption edge occurs. So you can see in the after graph only K alpha remains and the K beta and the white radiation coming after the strong K absorption edge comes, they all get absorbed and get removed due to the usage of this nickel filter. Now, in general, the rule is simple. To filter out K beta radiation from the target with atomic number Z, we use a foil with atomic number Z minus 1. So for molybdenum, which have a atomic number of 42, we use niobium, which have an atomic number of 41. This ensures that the beam we use for diffraction behaves as if it's truly monochromatic, giving sharp and reliable diffraction data. So the key takeaway from here is that filters make our X-ray source effectively monochromatic by removing the unwanted K beta, allowing the only strong stable K alpha radiation to reach the crystal. Now in the last slide we have seen how we can use filters to remove the unwanted K beta radiation and obtain an almost monochromatic X-ray beam. But filters only improve purity to a certain extent. If we want an even more precisely monochromatic beam, we use something called as crystal monochromator. A monochromator is basically a crystal, often made of graphite, that acts like a prism for X-rays. Just as a glass prism separates the white light into 7 different colors based on wavelength, a crystal separates X-rays of different wavelength by the diffraction at different angles. So, here you can see a flat crystal monochromator. Here is a polychromatic X-ray beam, which means it contains many wavelengths which strikes the crystal at a certain angle. The crystal has a parallel atomic plane here shown as the lines in the crystals which have d spacing of DHKL. And according to Bragg's law, only those X-rays that satisfy the condition of n lambda is equal to 2d sine theta will be diffracted at a specific angle theta. So what happens is, out of all the wavelength coming in, only one wavelength, say K alpha, will satisfy the Bragg's condition at this particular angle and it will get diffracted. Only the radiation which satisfy the Bragg's law will get diffracted from this flat crystal. That diffracted beam is your monochromatic X-ray, a pure single wavelength beam. So the flat crystal works as a selector. It lets us pick one particular wavelength from a mixed beam just by adjusting the diffraction angle. Now if we see here curved crystal monochromator, when you bend the crystal into a certain radius, here shown as 2r, it helps to focus the diffracted rays to a common point called as approximate focus. This setup gives a stronger and more focused monochromatic beam because the curvature helps collect more X-ray over wider area and bring them together. Wider area and brings them together. Basically, it composes of more X-rays which are incidented on it. So while a flat crystal selects the wavelength, a curved crystal does the same thing but also focus the beam, giving us higher intensity and a better quality. This is especially useful in high precision X-ray diffraction experiment like single crystal XRD setups. So a filter can roughly remove unwanted wavelengths like K beta and the white radiation, but a crystal monochromator can precisely select only one wavelength, usually K alpha, making the beam truly monochromatic. And by curving the crystal, we can also focus that beam for better intensity. So now that we have talked about the conventional X-ray sources like cathode ray tube in very early slides and rotating anodes, let's move to something which is more powerful, and that is synchrotron. Synchrotron uh, radiation source. So what exactly is a synchrotron? A synchrotron is a huge circular accelerator where electrons are accelerated to nearly the speed of light, and these high speed electrons are made to travel in a circular path using a very strong magnetic field. Now, as the electrons bend around the circular track, they emit intense electromagnetic radiation, and that radiation includes very bright X-ray, and this is what we call synchrotron radiation. So uh, let's see a small animation on how synchrotron works. So in this animation, uh, we will see how a synchrotron works.
An electron gun fires bunches
So
of
this
electrons
is
through steel
electron
tubes
gun
into the
fire
booster
bunches
ring.
of electrons through
Microwave
steel
energy
tubes
is
into
then
the
used to
booster ring.
accelerate the electrons
And
up to
the
nearly the speed of
microwave
light.
energy
The
is
electron
then
beam is
used
then
to
injected into
accelerate
the
the
synchrotron
electron up
storage
to
ring.
nearly the speed
When the
of light.
path of these high-speed,
The
high-energy
electron
electrons is
beam is
bent by
then
magnets
injected
inside
into
the
the
storage
synchrotron
ring, a
storage
natural
ring. When the
phenomenon
path
occurs
of
to
these
produce an
high
extremely
speed
brilliant light.
energy
Beam lines
electron is
capture,
bent by
manipulate,
magnet
and
inside
direct
the
this light
storage
onto
ring.
samples.
A natural
The interaction of light with molecules in
phenomenon occur to produce an extremely bright, brilliant light. So,
the samples
in
allow
this animation,
gun
here
fires
you
bunches
see
of
that how
electrons
the
through steel
electron
tubes
comes
into
and
the
it
booster
travels
ring.
into a circular
Microwave
path
energy is then used to
in these
accelerate the
steel tubes, this
electrons up to
circular
nearly
path.
the speed of light.
It
The
travels
electron
in this
beam is then
circular
injected
path,
into the
and
synchrotron
as
storage
it
ring.
is
When the
deflected by
path of
these
these high-speed,
magnets,
high-energy electrons
so
is bent
its
by
path
magnets inside the
changes,
storage
and
ring,
due
a
to
natural
which the
phenomenon
X-ray is
occurs to
generated. You can
produce
see
an
this white dot
extremely
is X-ray
brilliant light.
radiation,
Beam lines
and
capture,
these
manipulate, and direct this light.
X-ray radiation then manipulate and direct this line onto the sample. This is the sample, and the interaction of light with the sample molecules allows
An
scientists to
electron gun
obtain
fires
very
bunches of
detailed
electrons through
image.
steel tubes into the booster ring. Microwave energy is then used to accelerate the electron.
Very detailed images of the molecular structure of material as well as a very detailed chemical analysis. So, in a normal X-ray tube, the X-rays come from sudden deceleration of electron hitting a metal target. The intensity is limited and beam can't be made extremely small or focused. But in synchrotron, the electrons are kept in circular continuous motion, radiating X-rays tangentially at every turn. These X-rays are extremely intense, like it is written here also, extremely intense, highly collimated, means the beams are very parallel and tunable. We can select any wavelength we need by adjusting the electron energy or magnet settings. So, why do we need synchrotron X-rays? We need them for very tiny crystal structure determination, like protein or nanomaterial crystal. Conventional sources are just too weak and the diffraction pattern is barely visible. But with extremely high intensity of synchrotron X-ray makes it possible to collect high quality diffraction data even from the crystals that are less than 0.05 millimeter in size. And that's why synchrotrons are considered the most advanced X-ray source, and they give us brightness, tunability and precision that no laboratory source can match. So to summarize, synchrotron accelerate electron to nearly speed of light first. Second, when electrons are bent by the magnets, they emit powerful X-ray radiation tangentially. And third, these X-rays are intense, focused and tunable, making them ideal for advanced research in crystallography, material science and biology. And that sums this up. Now, this synchrotron radiation was actually used to determine the structure of ribosome. To determine the structure of ribosome, the scientists used extremely intense X-rays from synchrotron radiation source, and these high brightness X-rays allowed the diffraction data to be collected from very tiny ribosome crystal that conventional X-ray tubes couldn't handle. Using this data, researcher maps the atomic structure of both ribosomal unit and both ribosomal units of a ribosome, that is 70s as a whole and 50s of a bigger uh, part of ribosome and 30s of the smaller part of the ribosome. Both structure was determined, revealing how ribosome reads mRNA and builds protein. And this discovery earned 2009 Nobel Prize in Chemistry. So we have learned that from these slides in this presentation, we have learned the X-rays are short wavelength electromagnetic waves. X-rays are an essential tool in exploring the atomic world. From their generation in the conventional X-ray cathode tubes to refining their properties, their purities using filters and monochromators, every step ensures we obtain a truly monochromatic and precise beam for diffraction studies. And with the development of powerful synchrotrons sources, we can now achieve extremely intense and focused X-rays, strong enough to reveal even the most complex biological structure like ribosomes. Altogether, these advancements have transformed X-ray diffraction into one of the most powerful techniques for understanding the matter at atomic level. Thank you.